Hello, this is your fourth video looking at the sun. We're going to be looking at solar activity, solar wind, and the effects on Earth, as well as some energy production within the sun. So the most obvious indication that solar activity affects Earthlings is aurora. Aurora is this visible effect of solar wind particles interacting with our magnetic field. And they're generally centered over the poles, or our magnetic poles, because we can remember that Earth is like a dipole magnet. When we have times of intense solar activity, the aurora can come further south, but generally on a regular basis, that's where they're seen. This is a pretty fantastic light show, and it's caused by these collisions between these electrically charged particles released from the sun as they enter Earth's atmosphere and they collide with gases like oxygen and nitrogen. If you ever have the opportunity to see them, they are pretty fantastic. And they're not stagnant. They move because, number one, Earth is rotating, and this is literally the bombardment of particles, which is not a static thing. The most common color is green. That's produced by oxygen molecules, and these are really high altitude, even though if you take a look at this image, it looks as though this is right at ground level. This is really up in the thermosphere, about 60 miles above Earth. So for comparison, our weather balloon will only go up to about 19 miles. So green is the most common, so as it's colliding with atomic oxygen. And sometimes these red auroras, which are more rare, can be produced by extremely high altitude oxygen, which generally is not found in high concentrations, and these can be found at heights of up to 200 miles. So these red aurora you can see are higher, but these are about 200 miles up, and it creates this optical illusion because this area is likely not polar, but it's looking towards a polar region. Nitrogen is what produces the blue and purple auroras that can often accompany the general green ones because the majority of our atmosphere is not oxygen, it is actually nitrogen. So times that we have enhanced solar activity, such as huge solar flares or large CMEs, this interaction between Earth's magnetic field can generate large electrical currents of up to 1 million megawatts of power. So when we have these, since this is a magnetic and electrical storm, you can have, during times of really strong solar activity, we can see increased auroras at lower latitudes. And we've seen that happen in the past. So the solar wind is this active process of the sun constantly losing mass. So the sun has this solar wind that is a very high velocity wind, and the sun is losing about 10 to 14% of its mass every single year. But there is consistent energy production within the sun to fulfill that gap. You can have storms, just like the sunspots, following that pattern that can last a couple of weeks. And the largest solar storm that we ever saw was the Carrington-Hudgens event of 1859. And because this is an electromagnetic event, this does interrupt electronic systems. At that time, it was just telegraph wires, which literally erupted them and started fires. If this were to happen today, this could affect the entire global power grid, and then again causing intense auroras at lower latitudes. So energy within the sun and then that ejected solar wind material can cause space weather storms that can upset our modern technology. So the obvious would be spacecraft malfunctions, so interrupting satellites, disrupting their connection with the ground and actually warping all of their electronic systems. So we could then have our communication systems as a result that would be disrupted. And this goes beyond just your cell phones. This would be navigational problems with planes. Every communication system on Earth is linked to something, for the most part, within space, and that links to navigation. So you could have massive grounding of every single airport. There can also be intensive power system damage. So this is a generator, and it can actually warp those. And we will talk about this more in class, but one of the major concerns is that if we disrupt the whole global power grid, or say in North America, that we don't have enough backup generators to support the number of people that we have. So we could have radio signals, communications that become disrupted, and then that magnetic field would cause this electrical damage. And we've seen this before. In 1989, Quebec experienced a large power outage for over 9 hours, and in some places, it was for days. And this was due to solar activity, a large solar storm where the most intense solar wind particles happened to be over this region. So we know this event has happened before, and this could happen again. Astronaut safety is also a huge concern when we talk about solar winds, because astronauts are already exposed to a higher amount of radiation because they're outside of the protective layer of our atmosphere. So in times of a large solar magnetic event, they would get much higher doses of radiation, and also cosmic radiation from the center of the galaxy. So for humans to travel to, say, the moon or Mars, we would really need to have better storm forecasting and prediction, as well as shielding materials to prevent radiation damage from astronauts that are in space. Another very commonly cited effect of solar activity is linkages to climate change. From studying ice cores, we can deduce this range of change in the sun's magnetic field, and we can also then correlate that to changes in Earth's temperature. So we can see that we do have some general correlation here, but these changes are extremely small scale. We'll talk about the Little Ice Age, but during that time we had cooling of about 0.2 degrees Celsius, but that was felt that had a large impact, and then on top of it there was a volcanic eruption right in the middle. So here we have about 400 years of sunspot observations, because people have been keeping track of these through telescopes for quite some time. Following the Carrington event, people realized that the sun was capable of producing these magnetic storms. So sunspot monitoring was something that was commonplace. So we can see that with increased counts, this also correlates with an increase in technology, so this is slightly subjective. But we can see that there is this slight increase in solar output from 1900 to 1950. A lot of that, again, is correlating with our increases in technology, but you can see that we have lower peaks in the periods of extremely warm years. So this argument really can't be used to influence arguments of climate change right now. So what's happening here is that the global magnetic field, when it's at a minimum, is actually weaker. So you have less solar wind that's impacting Earth. So times when you have greater sunspots, remember that those are cooler regions of the sun, but you have warmer regions surrounding them. So times of sunspots, increased sunspots are correlated with an increase in temperature. And this area called the Maunder Minimum, or where the Little Ice Age took place, is associated with fewer sunspots. So although the Maunder Minimum, which is that couple 100-year period, is commonly cited as a time of low sunspots and lower temperatures, we also had a time called the Dalton Minimum, which is only about a 30-year period. And this is an image that someone painted at the time that they called a year without the summer. This is a view of the frozen river. So this is in 1914. So this was in 1816 that there was the year without the summer, but just the year previous to that, the Tambora volcano erupted, and that then covered the sky in soot. It blocked photosynthetic activity, kept plants from growing. So then you had massive amounts of malnutrition, people dying from that. Then you had the bubonic plague. So it became this very cyclical event that may have started with solar flares, but then on top of it, we had this volcanic eruption that caused about a third of the people in Europe to die at that time. So the next thing that we are going to look at is energy production within the sun and all stars. And in order to be actually called a star, it has to be hot enough to induce nuclear fusion at the core. So we know that that takes about 1,000,000 degrees Kelvin, and that is when the star becomes radiative in the visible portion of the spectra. Prior to that, it would only be seen in infrared. So we have stars that can spend millions and hundreds of millions of years only visible in infrared and enshrouded by a dust cocoon, only seen beyond that in infrared wavelengths. And then we say the star is born when it completes fusion. So we have a large amount of stars that look kind of like Jupiter does, and we call those brown dwarfs. They're not quite hot enough to be a star yet. So in stars like our sun, we have fusion that is known as the proton-to-proton chain. This is where we have the interchange between hydrogen atoms into heavier helium atoms. So fusion is the combining together of light atoms to get heavier elements. So in the sun, this is always going to be hydrogen to helium until it gets to a later phase in its life. And then the byproduct of that is also energy. And Einstein's famous equation is this fundamental concept where we see that mass and energy are interchangeable. So I think I previously said 1,000,000 degrees. Some accounts say that, others say 15 million. And that's the temperature you have to have in order to ignite fusion. Here is the actual chemical rundown. And that energy is coming from the mass of those 4 hydrogen atoms that is then going to produce 1 helium atom. So here we can kind of see a little diagram of that, our 4 hydrogens. Our byproduct is a neutrino and energy, and then we have helium-4. So one thing that is kind of interesting is that helium-3 is a solar wind byproduct that gets implanted in every planetary surface. On Earth, our atmosphere really blocks that, but on places like the moon and on asteroids, there is a high degree of helium-3, which can be used as a much more sustainable, higher energy source for things like propellant, so much more so than fossil fuels could. So one big push to get settlements on the moon would be to extract that helium to then use as a sustainable energy source here on Earth. It's in much higher abundance on the moon than fossil fuels are here. So I've talked about combining together of 4 hydrogen atoms, and hopefully something that maybe jarred in your brain was that these are like elements. Not supposed to happen. Positives don't attract positives. They attract opposite elements. So they shouldn't bond with the exact same thing. So what that is called is overcoming the Coulomb barrier, which is the necessary heat and energy it takes to bind together elements that are alike, and that takes extremely high temperatures and extremely high pressures. So that is what the core of the sun can provide, and that's why you have to have this particular temperature in order to do that. Otherwise, it's not hot enough to overcome that barrier. So just for comparison, 1 second of our sun, we have over 1,000 reactions that take place. 600 billion kilograms of hydrogen is converted to helium, and we have about 4 billion kilograms of mass that is then converted to energy. So this energy production is what overcomes that mass loss in the sun due to the solar wind. So in the sun, we call this reaction the proton-to-proton chain, the combining together of hydrogen to get helium, which is not the same process as what we have in other stars. We say that stars that are generally greater than 8 solar masses are massive stars. So we break stars into 2 categories, sun-like stars and massive stars. So sun being our basis of all comparison, and then greater than 8 solar masses would be our massive stars. And massive stars follow a different cycle. We call this the CNO for carbon, nitrogen, oxygen cycle, whereas in sun-like stars, it's the proton-to-proton chain. It's a cyclical pattern within more massive stars. So more massive stars, mass is correlated with temperature. So more massive stars have a higher temperature. So when they emerge from their dusty infrared cloud, they're going to have a higher mass, higher temperature, and they actually start life that way. They don't grow to be that. That is how they begin their life. Like some kids are born bigger than others. These stars are the big kids of the universe. So in the CNO cycle, unlike the proton-to-proton chain, this is converting hydrogen to helium, so that process is still happening, lighter to heavier, but it's in a catalytic fashion. So the oxygen doesn't have to be stable in order to produce energy. So this then converts lighter elements to heavier elements. You end up having nitrogen-13 that's unstable. It decays to an isotope of carbon. That isotope of carbon captures a proton, and that becomes an isotope of nitrogen. That isotope of nitrogen captures another proton, and that decays to an isotope of oxygen, hence CNO. That mass isotope of oxygen undergoes a beta decay, and it becomes another isotope of nitrogen. That isotope captures another proton, and it closes the cycle to return back to carbon. So within more massive stars, you have more elements that are present all at the same time, whereas in a sun-like star, for most of its life, it is just happily fusing hydrogen to helium. And then the content of within the star is becoming more hydrogen deficient, and you have more of a surplus of helium. Whereas in these heavier stars, you have this simultaneous reaction that's producing multiple different elements in addition to helium. This concept of nucleosynthesis is this constant cycling and recycling of lighter elements into heavier elements and then cycling them from one star's death into another star's birth. So in the Big Bang, we had nucleosynthesis that was responsible for the very first atoms and nuclei, and that happened within the first seconds. But what happens now is we have supernova nucleosynthesis, and this is delivering all elements that are heavier than magnesium into the interstellar medium because the sun is not capable of producing those. But we can see if we take a look at the interior composition of a heavier star that we have all of these heavier elements. So in addition to hydrogen and helium, we have things like neon, magnesium, silicon, and the heaviest stars will produce iron at their core, which is how we get iron delivered everywhere in the universe, including the iron within your blood. It is all from exploding stars. And on the opposite end of that spectrum, we have stars smaller than the sun. Approximately 8% of the sun's mass we would call that a brown dwarf. And these look very much like Jupiter. So we can say with confidence that our sun is stable. It is not getting any bigger. It is not getting any hotter. It is stable for the majority of its life. We can think about this as being like the middle age of a star. So during this time, the sun is stable because we have a process called hydrostatic equilibrium. So this is essentially when the outward push of fusion is balanced with the inward gas pressure force of gravity. So we have the force of gravity that is directed towards the center, and that opposing force is the gas pressure that is pushing out from the energy production of fusion. So even though the gravitational force can cause the star to collapse, the pressure then increases and forces that gas back out. And in the case of our sun, it will continue doing this delicate balance, this dance between forces for about 10 billion years. So our sun is only about 5 billion years old. It's got a long time before there's going to be any change within the sun. There will still be this equilibrium and balance. That is it for your notes. I'll see you in class.